All right. So the last item I'd like to talk about, and that you can also bring to your classrooms for your students, better understanding and exposure, is this website, this wonderful website, Myscope, that gives you a chance to be more familiar with many of these nanocharacterization tools. We'll go over some of them here listed. The first one is a scanning electron microscope. And in here, you can reach the SPM Simulator, and it will take you to this website where you can really follow the steps here. If you're not very much familiar with SPM, they will already tell you what to do next. First, we'll start by venting the tool. And this is now showing us inside the chamber of the SPM. We have the electron beam column here, and the detectors are located. The sample state is here. After venting the chamber, the user needs to open the chamber to locate the samples. And then we'll need to close the samples door and pump down the chamber again to start the electron beam examination, which is evacuating the chamber. Now, it asks us to choose between different samples like wood, pollen, rock, and steel. Let's go with wood. Right. Now, we're going to have to accelerate the electrons from the gun column to start visualization. And we can start by 10 kilovolts. Okay, so that's the energy of the electrons coming in. And we'll need to initiate the beam. So HD should be turned on. And at this point, gives us this kind of a warning and saying, yeah, you can do whatever you like to do. Right. Now we're collecting some images from the sample, which is the wood sample, but it's kind of dark. So it's also pretty far away from the my electron beam column. I'll need to adjust my working distance to get better images. Like I move it up to the stage up by 20 centimeters, 20 millimeters, sorry, and then put it to a working distance of 5 millimeters. That's the distance between the my objective lens in my electron beam column and my sample. Now I can make it 0 too, but that would crush the sample into the electron beam column, which would also be a nice demonstration for our students that we cannot realize in real life because that would be very, very costly. But the students can see that we can damage the tool by just working around with the different working distances chosen here. Now I need to refocus the image, but I can also increase this contrast a bit. So improving the contrast with these using the knob, so I can first give it a bit of a brightness like here. Okay, and let's magnify the image. So I'm kind of showing you the capabilities of the tool, virtual tool. All right, now we're really going into a higher magnification. And the students can follow what's going on by also following up the scale bar here. Now that scale bar is getting larger, and that's now equal to 20 micrometers. So we can adjust our contrast. And we may want to refocus a bit. So these are the focusing knobs. Just to get a slightly better image. And that's the coarse focusing, so you can start to do the fine tuning by adjusting the fine focusing knob as much as you can. And the students will appreciate that. Okay, so there's a sweet spot of focusing or these readjustments by moving around the knobs, and then they will have to figure that out. That's sweet spot. And you can work around with the astigmation tools to get a slightly better image. These magnifications are not drastically large to really start feeling the importance of astigmation yet, but still stigmatism and stigmation tools are quite important. So, yeah. Okay, so, and you can also highlight that we can get a better image by slowing the scan speed, so they can see how slow the image scan will take place. Now it's an enhanced image because we're scanning the surface much better, much slower. And again, just like AFM, we're losing the throughput, but getting a better image. And we can also emphasize that this is a secondary electron image by showing them that this is coming from SE rather than a backscattered electron image. So I'd like to do a backscattered electron examination just to show you what the tool can do. So I'll stop the HT and I'll switch to, say, the steel. So that's now turning around the samples, and I'm gonna improve the acceleration voltage for a backscattered electron. All right, so now we're looking at the steel, and I will increase the working distance once more. This is the spot size, by the way. I can try to work with different spot sizes here. The smallest spot size is expected to give us the best resolution. So moving around my brightness and contrast. Okay, and then the magnification one more time. So improving the magnification. Okay, and then trying to work out the focusing one more time. I guess it's a slightly better focus right now. Again, the slow scan speed. But that's pretty slow for our discussion, so let me just switch to the normal TV rate. So from scanning a secondary electron to backscattered electrons, once we turn that into backscattered electrons, yeah, we see a different image. And this different image is now telling us something about the compositional information of the steel. The dark spots are not giving us enough intensity of the backscattered electrons, where there's like lots of bright spots here. The bright spots are telling us that those are either dense configurations of the atoms located, or there's like more higher atomic number particles located in those areas. So we get a more understanding about the nano characterization and nano seeing the samples. Now, this is the SEM tool. Let's switch to the other properties of that are available here. How about the energy dispersive spectroscopy? EDS Simulator. So that's going to be great because it's going to take us immediately to the same sample, the steel sample, and we're going to now look at the Xray spectroscopy. So that's the same steel sample, and we're starting to get some X-ray emission when we send our electron beam, and the students can look at the periodic table and label the emissions accordingly. So we can see that we're getting like quite a bit of iron and also titanium together with lower atomic number elements. And we can get like a elemental compositional information So the elemental maps are created. We see that we got like aluminum and iron, both shown here. So this is our backscattered electron image, and in the backscattered electron image, we get like these areas to be darker, whereas these areas to be much brighter. And that's also highlighted here as we got lots of titanium and iron in those areas that are brighter compared to the cases where we get the aluminum. Aluminum has a lower atomic number compared to iron and titanium. Will of course give us a darker area under backscattered electron emission. So these maps are also showing our students a much better understanding. And one other thing that we can do is, again, by activating the EDS simulator. Now, point-wise analysis to do a quantitative analysis. So I can take a point like from there, any point that I choose, and I can get the emissions from that particular point and label them on the elemental periodic table. And I see that I got like a huge titanium and iron because I got it from here, which I knew already that was rich with titanium and iron. And a semi-quantitative analysis gives me the weight and atomic distribution percentages. So weight-wise, I got 30% of that area at that point to be coming from oxygen, 2% or 3% say magnesium. Titanium and iron is like higher than 30%, but that made up a rich area, rich point for my titanium and iron concentration. And I can choose different spots on the same sample and analyze them, and let my students see and understand how this EDS is working for us to understand the chemical components of the materials. So the students can see in summary secondary electron emission, backscattered electron emission, and also the EDS analysis, and understand it within the main framework of scanning electron microscopy. Another thing that we can do is, after talking a lot about AFM, so we can do an SPM simulator, scanning probe microscopy and analysis, or nanotubes, so with the help of an AFM tool here. So let's make this full screen. So again, the tool will tell us like the directions, what to do next. So we can now analyze or scan a nanotube, a nanowire, with the help of an AFM tip. We'll choose a tapping mode, which will be a mode that is most appropriate for these kind of scans for nanoscale features. So like you can see, we need to align the laser. So we'll follow the steps one by one. We'll put the laser on the cantilever beam so that we can get the laser pointing, shining to the mid spot of the photodetectors. We'll use the diode X and Y to put the beam in the midpoint like this. So now we'll tune the target amplitude to 500 millivolts. So that's the, like you can see, the vendor company suggests that information. Now we need to set a frequency range to identify the tapping mode's natural resonance frequency of the cantilever beam. So for those folks who are already familiar, will immediately recognize what I'm doing right now. I'm trying to sort out the natural resonance frequency of the AFM tip. So let's auto-tune this and we'll hopefully find it. Yes, we've just found it to be close to 350 kilohertz. We'll select the scan size. Let's say 1 micrometer. Let's select an integral gain, not too high. And proportional gain, again, not too high. We know what will go wrong if we set it too high. Will be unstable. Set the scan rate, so I would like to get a decent resolution. So 1 scan per line, one line per second, so that's equal to 1 Hertz. If I increase this number, it will get quicker, but it will lose its resolution, just like we analyzed with Veda. And I'll need to set my set points. So that's going to be the swings that I will locate. So I don't want it to be as wild as 500 millivolts, but like something like a half number to 70. Okay, so we're going to put the laser beam relative to the set points, the right in the middle. We're going to use the motors to move the cantilever beam closer to the sample. And around here, we will use an Autoengage button because they're really within the vicinity of each other. They're very close to each other. And once we hit the engage button, it will engage the tip with the sample. So maybe a bit more, and then engage now, yes. So it's auto-engaging. Now we're going to start the scan. And as we're scanning, we're collecting some information line by line, and that information is summed up. Like you can see, we're getting an amplitude modulation. So our tip is scanning across and is moving up and down. And by moving it up and down with that kind of a vibration, we can understand what kind of features we have. If the overall amplitude modulation is of this kind of a 270 millivolts is not satisfied, so that means we need to give the feedback to keep it at that kind of a tapping mode, amplitude modulation constant. In other words, if I happen to stumble across these kind of nanowires, I need to readjust the position of my stage or my tip with the help of a feedback loop, and that helps me to still be in the vicinity of the sample, but readjust the position so I can get the full swing of this kind of a modulation. And I'm gathering my sample image line by line, one line in 1 second. And the students can appreciate and understand like what kind of images we can obtain. These are now, we're looking at these nanowires, and they can also figure out how long it will take to get this whole image, because we're scanning a 1 micrometer by 1 micrometer area, 1 micrometer square area. And we're partitioning that into several lines. And we're scanning one line per second. So the image has been collected, so we can save this image and save that to our computer. We can do this imaging for different scan rates and see the difference in the resolution that we will attain. We can scan at different scan sizes, and we can, like, say, focus onto a smaller area or a larger area and see the differences too, or change the gains and then see how that will alter all these things. And we can real time see as we're scanning across, so how that nanotube is altering the on the x-axis while we're scanning, altering the positions, altering the image information of my AFM. Okay, and then we'll have to disengage the tip, of course. So you can see the optical microscope imaging here. And we just disengaged. We can engage again, so that's now in focus. If we disengage, that's going to be out of focus. And we're using the motor, we can really pull it up and take my sample out and take my beam, cantilever beam out without damaging each one of these things there. All right, so one last thing I would like to talk about is the XRD simulator. X-ray diffraction tool. Okay, let me pause the video here. Apparently something is going wrong. Yeah, so the last thing I would like to emphasize, their X-ray diffraction simulator, that you can also carry out the simple experiment in your classroom with your students, where you have this simulator and the X-ray is coming from this direction and is received by this direction. Fortunately now, at this time being, I think they're going through some website repairs, so I couldn't get the simulator work, but it's located on that side, and the applet looks like this. So, and once you turn on the power, once you select the start and end angles, and also entry slit, and the time per step while your sample is located here, and the source is your X-ray source that you'll send with, and you will start to see some peaks occurring here as a measurement with respect to the incoming angle. And those peaks will, of course, show you the information that you're curious about regarding the crystal orientation of the sample, also to diagnose or to understand what kind of sample you're looking at. All right, so this sums up the nice tools that are located on Myscope. So hopefully you'll check it out. Thank you.